now comes backpropagation learning. Okay, so till now we were discussing that uh, you know all the values or all the outputs from the previous layers are sent in the forward direction only. They are passed in the forward direction. But we have something called backpropagation learning. By using that, our network will learn very efficiently and very accurately. It will work very efficiently and accurately on any level of non-linearity. Okay, so the purpose of backpropagation learning is to update the weights basically. As I told you, no, see, if the uh, actual value is say 10, predicted value is 8, there is a difference of 2, right? Minus 2, say, between a minus b, actual minus predicted. There is difference of 2 units. Then what should happen? The weight should be increased, right? So that when the weight will be increased, whenever you will provide the actual value, or say all the input feature vector x, it will again be multiplied with some higher value so that it will match your actual value. And suppose next time you got 9.5 after updating the weight. How these weights are getting updated? These weights are updated based on the error at the output layer. Whatever the error we are getting at the output layer, those error or those loss function will decide how much we should update the weight. Correct? So this is called basically the backpropagation, where we will backpropagate the error to the previous layers, previous nodes, right? And by using the backpropagation, by backpropagating the error to the previous nodes, we will update the weight. How much is the error at the output layer? How much error is at the output layer, and based on those errors we will need to update the weights in the previous layers, and the network will again start from the beginning after updating all the weights. So there are multiple ways to update the weights, like batch updation, mini batch updation, stochastic. There are different things. Online updation. There are different ways, right? Which we will discuss later. But for time being, just saying that we will need to update this weight so that the error will be minimum. And this process of back propagating the error back to the previous layers is called back propagation learning. Okay, so here in back propagation learning, we have 4 different scenarios, as seen, I have mentioned in the PPT here slide. Single layer network, where we will see the scenario of single output with non-linearity, like non-linear function. I'll use any non-linear function. Sorry, without non-linearity. Okay, we will use the single output layer without non-linearity. It means we can use simple functions like threshold function kind of thing. Again, in the next scenario, we will see single output with non-linearity. First one is without non-linearity, second is with non-linearity. The next scenario, we will see multiple outputs with non-linearity, and finally we will see multiple output for hidden layers. How backpropagation happens in hidden layers. We will see all these scenarios. We'll start our discussion with single output without non-linearity. Okay, so this is a very simple one. We will discuss first. So given a neural network with single neuron, which will take multiple inputs like this one. Okay, this is a xi, and some weight will be applied to the xi and some function here, whatever the function. So it will give some output value y hat. Y hat means what? The predicted value, estimated value from the network, and it will be given as w transpose say xi. Okay, now since this is very simple, okay, just think we have considered a very simple network. That means a single layer network where the weight vector W and some input feature vector xi. And as we have already discussed earlier, that the simplest network with only one layer can solve only linear problems, not non-linear problems, right? So if we feed an input vector, say xi, we expect that the output should be yi. And only when we get the output as yi, which matches with the true value, means actual value. It should match the yi had, should match the actual value. Then at least this xi value, this input feature vector xi, is correctly classified by our this neural network. But what we actually get is we will get some predicted value which has some probability of error. Correct? So basically this yi hat, which is given as w transpose xi, is nothing but the approximation to yi, the actual value yi. This is just an approximation to yi hat, right? And if yi hat and yi are same, then xi is correctly classified. And if we don't need to modify the weight vector w. In case when yi and yi hat both are same, then why do we need to modify this one? We don't need to modify, right? Now suppose this yi and yi hat are not same, so there will be some error, and in that case the error is given by some loss function as 1 by 2 summation of this output. What is the output? W transpose xi. This is t, okay? W transpose xi minus the actual value yi, and we'll take the square, right? Which we can also write as this one is nothing but yi hat. Yi hat. Same thing. Okay. Now this the summation will be from I equals to 1 to n, total number of observations, right? Now tell me one thing. Here we are sending the error. Sorry, we are scaling the error. We are not sending. We are just scaling this error, the entire error, by 1 by 2. So do you guys remember from yesterday's class why we used to scale this error? The reason behind this scaling? Anyone? Do you guys remember why we were scaling, why we are adding this 1 by 2, one factor 1 by 2 against the error or loss function?
Like derivative would cancel out.
Yeah, correct. This will basically make our, this error function or the loss function very simpler. That's why. Nothing else, no other reason. Okay. Now, the error will be minimum. Then only our network is good. Okay. What value of weight? The error value will be minimum. Okay. So basically, we are interested in updating the weight. So we have to update the weight in order to minimize the total error E, which is given by this equation. This is E is nothing but your loss function. You can also say loss function. Okay, the loss function is given by this equation, these terms, and to minimize this loss function, we have to keep updating this W or the weight. And so the weight updation rule will follow the weight updation procedure. It means we have to regularly update the weights for the network. Correct? Now, when we take the derivative of this one, del E, partial derivative of E with respect to W, this weight, which is will be given as summation of I equals to 1 to N. What will there? Yi minus yi hat minus yi into xi, this xi. Correct, guys? Am I good? We are taking the derivative with respect to W, right? So first we need to take this one. So this 2 and 2 will be cancelled out, right? When we take the internal part, then this will be xi only, right? So we are multiplying by xi. Okay, and this time will be 0 minus 0. So this one will be left minus 0. So minus 0 we are not writing. Okay, now the weight, the new weight is given as, we are in the process of updating the weights for the network, right? When we have got some error, what we'll do is we'll back propagate the error back to the network, and we'll ask the network to update the weight so that the next time error will be minimum. And that's why we are taking the gradient, we are taking the derivative of error. Why? To find the minimum error with respect to what? E. At what value of weight? We are actually interested in the values of weight that will minimize my error, right? So with respect to weight, I am differentiating it. We are taking the derivative of this error loss function E, and by that every time the weight will be updated until and unless the error is minimum. So at every iteration we will have the values of weight. Weight will be updated by W minus some eta times the derivative, that daily, whatever the daily is there, from I equals to 1 to n, same, and it will be yi hat minus yi times xi. Okay, what is this eta? Okay, so this eta is nothing but rate of convergence. Rate of convergence. This eta is nothing but the rate of convergence. It is a factor, it is a constant value. So when the value of this eta is high, the rate of convergence will be faster, right? And when the value of this eta is very low, the rate of convergence will be slow. Is it clear, guys? Rate of convergence. Convergence means what? How soon the network will be stabilized or your training will be completed. The training of the network will be completed. How soon? That is basically decided by this term eta, some constant. When the value of eta is higher, it means W minus some higher value. Right? So the rate of convergence will be faster. When the value of eta is very low, say 0.001, every time we will be adding or subtracting to the new weight, the updated weight, right? So the addition or subtraction of very less value to the previous weight value, I mean, it will just delay your training time, right? It will just take more and more amount of time to converge the network. Okay, so the value of eta basically will decide the rate of convergence of the network. If W transpose X is greater than 0, say W transpose X is greater than 0. So in that case, this Yi will belong to which class? Yi will, I'll simply write Yi will belong to, say, positive class, plus 1. I'm assuming initially that If W transpose X is greater than 0, it belongs to some class, say class 1. And if W transpose X is less than 0, then it will belong to some another class. So I am considering here that, say, if W transpose X greater than 0, then Yi will belong to, say, positive class, which I am giving name as, say, omega 1. Okay. So now since we have W updated weight equals to W minus eta times the summation of I equals to 1 to n yi minus y hat, this one, into xi, right? Now suppose if yi belongs to positive plus 1 class but yi hat is negative, that means W transpose X should be greater than 0, correct or not? But it happens to be less than 0. It means it will belong to negative class. But actually it should belongs to positive class. In that case, your entire term, this term in the weight updation rule, I'm saying the entire term will be negative. Correct or not? Negative, some negative value minus positive value. What will happen? Some negative, right? And then in that case, the weight, the updated weight is given as the previous weight plus y plus this minus the entire thing will give you the negative part. So minus minus plus eta times summation of I equals to 1 to n yi hat minus yi into xi. It means that when the xi is misclassified, then we are adding a fraction of xi to update the weight vector. We are adding a fraction of xi. Can you see here? Addition we are doing. In the same manner, if we assume that yi is 0, but we get yi to be positive, means greater than 0, means again misclassification. Then also this xi is misclassified, and again the weight vector, the updated weight vector w will be given as the previous weight plus eta times I equals to 1 to n yi hat minus yi times xi. And also we are adding the fraction of xi, fraction of negated xy. Sorry, it will be negative here, guys. Sorry, it's my bad. Anyway, okay, so we are basically adding the negated value of xi, some fraction of negated xi to w to update the weight vector. So in both the cases here, that's why we have in the formula that negative sign here. That is the importance of this one. Okay, so when there is some misclassification from positive to negative or negative to positive, this is a actual value, this is a predicted value. Okay, suppose actual value is positive but we are getting negative, right? In that case, some fraction of xi means input value will be added, because this will be minus minus plus here. Some fraction of this input feature vector xi will be added to update the weight. In other case, when we have the misclassifications within the neural network, this is the way we have to update the weight. So in interview, I'll talk about some important questions also. So in an interview, they may ask this kind of, how do you update the weight? Now if someone will ask me how to select the initial weight w, okay, that we will discuss later. Okay, so for timing, this w actually is selected randomly, any value between 0 to 1, not 0, not 1, any value between 0 to 1 initially. Okay, now we'll discuss single output with non-linearity. Okay, where it has been given that suppose we have some neuron which will take multiple inputs as a feature vector, say xi, and we have some weight here. Okay, this neuron will output something, some yi hat, which will be non-linear. So in case of non-linear, suppose we take sigmoid function, which is non-linear. Now this sigmoid function will take w transpose x, the same thing. Okay, now the sigmoid function is given as 1 by 1 plus e to the power minus s, as we know that, right? So we can, this sigmoid function, if you remember, this one was like this, right? This one be 1. Okay, 1. This one will be 0.5 and 0. And here in the x-axis we have w transpose x, and in the y-axis we have the sigmoid function of w transpose x. Okay, so suppose that instead of using any threshold function at the output layer here, which is basically non-differentiable, we are now using sigmoidal function at the output layer for a single layer network, which will be differentiable because this sigmoidal function is differentiable. In our case, this S is nothing but W transpose X. So S equals to W transpose X. So at S equals to 0, this sigmoidal function value will output as 0.5. And when S tends to infinity, this sigmoid the sigmoidal function S will tend to plus 1, and when S tends to minus infinity, this function will tend to how much? 0. Okay, so we can see that when S increases on the positive side, right, the sigmoidal function asymptotically reaches the value 1, and when S decreases on the negative hand side, the sigmoidal function sigma S asymptotically reaches the value 0 here, right? The other advantage of using this sigmoidal function is that this is differentiable, right? And when we take the differentiation of the partial differentiation of the sigmoidal function, like this one, sigmoidal of S with respect to del S, then it will yield sigma S into 1 minus sigma S. Okay, which becomes in a very simple form basically. Okay, from here to here. How did we get that? We can use the same chain rule here. Okay, so these are the advantages of using our sigmoidal function as the activation function or non-linear function. Okay, so given this kind of neural network, okay, given this kind of scenario, let's see how to train a neural network with some sigmoidal function as a non-linear function or activation function. So let's assume here, given this one, can't go back again and again, so I'm drawing it again, this yi hat, okay, sigma w transpose x xi, okay, here will be xi. Okay, so now let's assume our training samples are given as ordered pair of feature vectors. As we saw, ordered pair means what? Xi comma yi. where xi is the input feature vector and yi is the corresponding class level for xi. Okay, so in this network, when we have single output with non-linearity, we feed in some input feature vector xi and get some output yi. We should get yi. Here, this sigma w transpose xi is used to impose non-linearity, as we are discussing with non-linearity output, non-linear output. So in this case, we have the error also, as we discussed earlier. Here also we'll be having some error. What will the error? Yi minus, or yi hat minus yi. Same error we'll be getting here also. Okay, so now again we can define some loss function e, which will be 1 by 2, same thing, summation of yi hat minus yi squared and I equals to 1 to n, same thing, which we can also write it as 1 by 2 summation of the sigma of w transpose xi minus yi square, I equals to 1 to n, same thing, right? So when we take the gradient of this loss function, this error function, we will have the gradient with respect to w, gradient of e, the loss function e, with respect to the weight w is given as the summation of I equals to 1 to n yi hat into 1 minus yi hat multiplied by yi hat minus yi into xi. Why? Because since we know that the partial differentiation of this sigmoid function with respect to this s is given as sigma s into 1 minus sigma s. And same thing we are putting here, sigma s minus 1 minus sigma s. Sigma s is nothing but yi hat, this one. Okay, now the weight updation rule here will be given as w, the new updated weight will be w minus eta times this same thing, the gradient of this error. What is the gradient of error? I equals to 1 to n, and we can take yi hat into 1 minus yi hat multiplied by yi hat minus yi hat yi into xi. This is the weight application rule in case of any non-linear scenario where we have the output in non-linear form. Yeah. So here now we will discuss with single layer with multiple output. Non-linearity will be there, single layer and multiple output. Okay, single layer, multiple output with non-linearity. Okay, now think in the previous case, it is very easy. We have single layer but multiple output. So suppose this is my input layer. Okay, so this one is the bias. I am providing xi feature vector xi to the model, to the input layers. Suppose this one the first neuron, second neuron, third neuron, all these things. Suppose this one is my ith neuron, guys. This one is my ith neuron. Okay, now, and this is a jth neuron, whatever. Now we have multiple outputs, single layer but with multiple outputs. So multiple outputs means what? I have more than one output, 1 2 say n, multiple outputs. And suppose this one is my jth layer, jth neuron, or say jth neuron. Okay. Now, in this case, when we are providing this one, all will be interconnected as we discussed with some weight. Correct. All will be interconnected with some weights. So here also it will be connected with all those three. Here also it will be connected with all the three. Okay. Now, since this is the ith neuron, this is the jth neuron at the output layer. Suppose this is my input layer and this is my output layer, where we have more than one outputs, right? So the connection, the weight connecting from ith neuron, okay, in the first layer, in the input layer with the jth neuron in the output layer is given by wij. wij. This is the weight from ith neuron to the jth neuron, right? Since we have only two layers here, input layer and output layer, that's why I'm writing only wij. Otherwise, I can also write the layers here. I'll show you. Okay. Now, in this case, this output at j, output at jth neuron is given by 1 by 1 plus e to the power theta, the same sigmoid function. Correct or not, guys? This output yi hat. Correct. Since we are discussing with non-linearity, this output at jth node is also given by something like this one. Now this theta j here, this theta j will be equal to how much? Summation of I equals to 1 to d, because d dimension is there, dimension of your input feature vector, and same thing, weight from I to j times xi. And here at that time, previously we used to take this theta or s whatever as w transpose x. Here also we are taking the w transpose x only. It is in a scalar form. So w, say we can take w transpose, that's fine, w transpose x, and this w is nothing but the connection from ith neuron to jth neuron, and I will now vary from 1 to d. D means what? All the input feature vectors. D is a d-dimensional feature vector, right? So this output j is given by 1 by 1 plus e to the power theta. This theta j is given by this value. Sorry, minus theta, I think, yeah, minus theta. Okay. Now, according to that, we can also have this loss function as 1 by 2 summation of j equals to 1 to m for oj, means output, minus tj. Tj I am saying as input, and we're taking the square. Same thing. oj is nothing but the output. oj is the output, the what do you say? The predicted output at jth node. Okay, and tj is the actual output at jth node. Same thing. Correct. Now, for the weight updation purpose, we have to take the derivative of dE with respect to this wij, which is now given as by chain rule, del E by del Oj multiplied by del Oj by del theta j multiplied by del theta j by del wij. This is nothing by your chain rule. That's why I told you guys to learn the chain rule, right? So first we will differentiate, we'll do the partial differentiation with respect to omega j, this oj. Second term, we'll differentiate this Oj with respect to theta j. Third term will differentiate this theta j with respect to the weight. So we had some function f, x, y, z, and we were taking the differentiation of the first with respect to x, then secondly with respect to y, and the third one with respect to z. Same thing we are doing it here according to the chain rule. Okay. Now this can be more simplified like del E upon del Wij will be given as Oj minus Tj multiplied by Oj into 1 minus Oj into Xi. We're just putting the values from here, from the sigmoidal function. When you differentiate the sigmoidal function, theta, this theta which you have, okay, when you differentiate this Oj with respect to theta j, okay, how much will we get? Similarly, this problem we can have the weight updation rule as well. The weight will be updated as weight Ij. Here also Ij. The updated weight will be Wij minus eta times this one, Oj minus Tj into Oj into 1 minus Oj into Xi. This will be my final in case of single layer and multiple outputs. This is just a generalization of the single layer with single output with non-linearity. We'll see for multi-layer perceptron. And multiple output. It is also very simple. The same way we will apply this. The only difference will be we will be having some input layer. Okay. We will be providing this x1, xi, and after that we will be having multiple layers in between. And finally, we'll be having this output layer. Say this is the output layer, this is the input layer. Okay, say this is a k minus 1, k k minus 1, k minus 2, and this is a output layer equals to k. This layer is named as k. Okay, now here also suppose this layer, this node is my ith neuron, and this ith neuron will connect to this jth neuron in the output layer. This is a jth neuron which will give me the output, final output. So this one I'm not connecting every node to make it simple, to look it simple. So this one is this one. Now I'll write this connection from ith neuron, okay, in the connection between ith neuron in the k minus 1th layer with jth neuron in the kth layer as this one. We write it like this one. It means whatever the output of this k minus 1th layer will be input of this kth layer in the jth neuron. And this output again is given by say Oj for kth layer. This is represented as this one. And here also this output at jth neuron in kth layer is given as 1 minus 1 plus e to the power minus theta in jth neuron for kth layer. Okay, and again if you simplify, this will be given as this theta value, this theta j in the kth node, this theta in the kth node is given as summation of wij in kth node multiplied by xi into k minus 1th node, because we are having multiple nodes here in between, multiple layers in between. So we are actually interested in these feature vectors. This will be my feature vector for the next output layer, not like this one. Here we had only one input layer and only one output layer, and in that case this xi was nothing but my input feature vector. But here the xi will take the form of the intermediate feature vector as an input feature vector for the output layer. Okay, and this is a mth node, sorry, mth layer. Sorry, this is the kth layer and m number of nodes are there, and this is the jth node or jth neuron, m number of neurons in kth layer. Okay, now similarly here sum of a squared error e, the loss function e, will be given as 1 by 2 the summation of oj k minus tj square, where j will vary from 1 to mk, means number of nodes in the kth layer. That's why I'm referring the m. E equals to 1 by 2 summation of ojk minus tj square, and j equals to 1 to m. Now here again I will take the partial difference dE with respect to del wij k. Okay, and it will again by differentiation rule here, sorry, the chain rule here, we'll take the partial differentiation as del E by del ojk into del ojk, this is j, divide upon it will be del with respect to theta, now del theta jk multiplied by del theta jk upon del wij according to the chain rule simply, which I can also write it as summation of j equals to 1 to mk, previously oj minus tj, or I can also write tjk, fine, into oj into 1 minus ojk into oi k minus 1. I'm not writing here, you know what I'm writing here? I'm writing O, means output from just the previous layer, not the xi. Correct? This xi I'm not writing as xi, I'm writing as what is the output from this previous layer. That's why I'm writing oi k minus 1. Right? We are calculating the error, basically the partial differences error with respect to w I j k. We are calculating it. We are finding the according to the we are finding that partial differentiation according to the chain rule, and in place of xi I am writing oi k minus 1. It means the input at the output layer will be the output from just the previous layer k minus 1th layer for ith neuron. That's why I'm writing this kind of thing. Okay. Now let I will make it more simple. So just let I will take another variable called delta jk equals to ojk multiplied by o minus ojk multiplied by ojk minus tj. And this one is nothing but this is the assumption which will be useful basically, which is just to simplify. That's it. So we can finally write this del E by del Wij will be equals to this one I equals to, oh my god, I equals to 1 to, sorry, j equals to 1 to mk, and this delta jk into oik minus 1, just to simplify this one. That's it. This is my differential total. And this, when I am assuming the delta jk is equals to this much, this will be more useful when we will calculate the weight updation rule for the hidden layers, because in the hidden layer it will be a bit complex. That's why we will just assume it. And finally, according to this one, the weight updation rule w will be given as wijk minus eta times this delta jk multiplied by oik minus 1. This is my weight updation rule, guys, for multi-layer perceptron with multiple outputs. Okay, concept is exactly same when we had some input feature vector, means input layer, and one output. Here we are having multiple outputs. That's why we have to calculate the error at all the output nodes, not a single output node. We have to take the summation of all the errors coming from all the output nodes. Okay, in case of single output node, we were interested in just calculating what is the output error. That's it. And we used to propagate it back by updating that weight, to update the weight. Here in this case, we are having multiple outputs. And in the output layer, and here in case we are having multiple layers as well. Multi-layer perceptron we are discussing. So in this case, the output at any layer, okay, j, the error at any layer jth, I mean output, the value of error for any jth node in the output layer will be given by this one, where oi is nothing but any output from k minus 1th layer in the from the ith node. See here, this input or this output will depend on ith neuron or ith node in k minus 1th node, sorry, k minus 1th layer, right? So this value, this output from this node will act as input for this output node. That's why we are writing this one, the input. This is actually deep learning, guys. Okay, in real. Okay, but the thing is to understand, to know the few basic concepts, why we are doing so, from where this concept is coming from. We just need to understand some basics, and these are the basics only. Okay, basics means what? How weights are updated at each one of the nodes in the output layer, hidden layer, any node. That's what we are more interested in, right? How weights are updated. Now we have multi-layer network. Here also we had multi-layer network previously, and here it will be multiple output. Okay, multi-layer network, multiple outputs with non-linearity, and we will discuss how to update the weights for hidden layers. It will be same, guys. Okay, suppose we have multiple inputs. Okay, now from the multiple inputs, suppose this is kth layer, and when we are interested in finding the weight backpropagated weight, updation of weight through backpropagation for the hidden layers, we will not be looking at input layers, right? We'll be looking at k minus 1th layer, plus 1th layer or kth layer. Okay. Now these are nothing but your different neurons in the hidden layer. Suppose there are three outputs here. Now this one is OJK. This is kth layer. This is k minus 1th layer. This is k minus 2th layer, and this is a input layer. Okay, ith layer or input layer. Oh, this something. Okay, this is input layer IP. Okay, now suppose this hidden layer in k minus 2, we have some hidden neuron called P neuron. We have some neuron which is called pth neuron in a hidden layer. Okay, this pth neuron is connected with ith neuron in the other hidden layer. Ith neuron with connection weight given as W k minus 1 pi. Okay, it is connected with the ith neuron, okay, in k minus 1th layer, correct, and pth neuron in the k minus 2nd layer. Now this ith neuron will again be connected with output layer, this layer, and this one, the weight is given as Wij, I to j, right? From I to j, it will be how much? Kth, yeah, sorry, kth node, yeah, kth layer in the output layer. Similarly, here also we can give the error function as E equals to 1 by 2 summation of Oj minus Tj, Ojk minus Tj square, and j will vary from j equals to 1 to number of nodes in the kth layer. Now to find the WPI, this guy, into k minus 1th layer, we had WPI, the connection weight from pth neuron in k minus 2nd layer to ith neuron in k minus 1 layer. To find this weight that minimizes E, that will minimize E, we find the gradient of E with respect to the weight from P to I in k minus 1th layer first, and output in the ith layer in k minus 1th, output at the ith node in k minus 1th layer is given as this ith, this one ith output, so that this output will again be sent as an input to the output layer. So this output I am talking, this output is given as minus 1 by 1 plus e to the power again minus theta ith neuron in k minus 1th layer, and this theta I k minus 1 is given as summation of WPI in k minus 1th layer into output for pth layer in k minus 2th layer. This will actually be the input in k minus 1st layer, and that's why the output from pth node in k minus 2nd layer will be the input for ith node in k minus first layer, and that's why the theta value is given like this one. So again, when we differentiate it, when we take the partial differentiation like this one, it will be given as del E by del OI k minus 1 multiplied by del OI k minus 1 divided by del W pi k minus 1. This is the chain rule. Sorry. Okay. Now this I can write it as del E by del W pi k minus 1 equals to del E by del OI k minus 1 into del OI k minus 1 upon del theta I k minus 1 multiplied by del theta I k minus 1 upon del W pi k minus 1. Okay. Similarly, we can write again this one as del E by del OI k minus 1 into del OI k minus 1 upon del theta I k minus 1, okay, into del theta I k minus 1 upon del W pi k minus 1 from the previous derivation from here guys, okay, not from here, here. From here we can write them in the new form, which will be like this one. Whole term, okay, we can write a OI k minus 1 multiplied by 1 minus OI k minus 1 into OP k minus 2. And for this one, for this term, for this individual term, I can give the value of this one as del E by del OJK multiplied by del OJK upon del theta JK into del theta JK upon del yeah, OI k minus 1, which can further be simplified as summation of j equals to 1 to mk oj k minus tj multiplied by oj k into 1 minus oj k into multiplied by wij, which we can again write it as this summation of delta jk into wij, simply when we consider the delta. Previously we had defined that OI k minus 1 equals to 1 by 1 plus e to the power minus theta I k minus 1. This was a defined one. Also, we can give the theta I k minus 1 equals to summation of WPI k minus 1 into OP k minus 2 for p equals to 1 to mk. Similarly, what we did here, we are replacing this one as this one. Previously, we have already seen that this E, when E is equals to 1 by 2 summation of minus tj square, okay, so where ojk is given as 1 by 1 plus e to the power minus theta jk, right? And this theta jk is also given as summation of wijk into oi k minus 1. And we assumed previously that the delta, this delta here, jk is given as ojk multiplied by 1 minus ojk into ojk minus tj. Previously, it's all, we assumed that delta jk. And we are just substituting the values, different values that we have already seen previously in the previous slides. Okay. So finally, what we can get it from here is, for hidden layer, the weight updation rule actually is given as for ith, for the connection between the ith node and jth node in kth layer is given as the previous weight minus eta times this delta jk into oi k minus 1. This is just the formula for updating the weight in any hidden layer. Okay, and this, if you want to expand it, then you can expand it. This delta jk, we assume that this is it is coming to jth, right? So it will be ith node, the previous node means input one, for k minus 1th node layer into 1 minus oi k minus 1, okay, into summation of j equals to 1 to mk, okay, delta j k wij. We are taking from here only. See, this value is nothing but this value. The entire value I am putting it here. Okay, so this is basically the weight updation rule for at any node in the hidden layer. Okay.